So let's start. Hi everyone, my name is Andrey. I'm working for Yandex Cloud. My day job is to work on Postgres, mostly fixing bugs of customers or working on improving scalability. My hobby is hacking on Postgres and exploring random ideas. Sometimes they have some meaning, sometimes they are mere technical joke. I maintain several open source tools like backup or connection pooling or sharding. Actually, most of this work is done by my team. Here, how we look like. Unfortunately, so far, only 3 of us are active on Hackers. It's very difficult to motivate youngsters to join mailing list and keep year-long discussions there, but I'm pushing them to do that. And today we are mostly talking about memory hierarchies. So when we are building a system that is working with data transformation, data storage, data searches, our task can be described as working with working set size of a lowest level with a performance of a highest level. And essentially, you can have big registers, you can have big caches, you can have big RAM, but it costs money. It's at the end of the day, it's economical trade-off that finally boils down to speed of the lights, but let's do not go that road, at least right now. There is another road that eventually we will have to discuss, is that this hierarchy doesn't end up on a block storage and we will have to go down too. But for the sake of simplicity, let's assume that we have this 4-level hierarchy. And the overall idea that I'm going to talk about is that cache line is the same idea of interface between hierarchy level as a storage page. So all the same ideas that we apply between file system and our access methods are applicable between cache lines and CPU registers. But in fact, most of wait time of CPU is not dictated by only cache misses when we somehow touched not that part of memory that we should, but there are also we have syscalls which cost about the same price as a cache miss do. We have branch misprediction, which is close in terms of nanoseconds to others, and we have log acquisitions which might seem even cheaper, but still they are close to the price of doing something wrong with on the border of central processor caches and main memory. If we look into well-known chart of latency numbers that every programmer should know, this is a joke. This is a joke, but not entirely a joke. What's interesting part? Here are numbers for CPU stuff and numbers for I/O stuff. It's for 2020. You will see why it's for 2020, not for 2024. Like I/O, network, SSDs, hard drives, and caches, mispredictions, syscall, mutexes. The very same picture for 10 years ago, and the very same picture for 20 years ago. Did you notice the difference? I'll flip there and back. There is none in the left side. So network is it's invisible for us, but network is getting better, lower latencies, and well, we can't have a faster light, but on other aspects we can have faster routing and other stuff. But our CPUs are essentially the same as they were 20 years ago. That's why in some recent years, recent 10 years, we saw the rise of so-called in-memory databases. And in fact, each one of them have a separate concept why they should be more efficient in terms of CPUs or caches. Some of them build their business on the idea that memory will get cheaper and cheaper and cheaper, which didn't happen, by the way. Memory is still costly. Some of them build their databases on ideas that you don't need locks when you have only one thread, and all other cool ideas to improve on that part that is not on that part of hardware that is not improving on this left part of a number that constrained us in building information systems. So, typical answer of a Postgresist who really loves Postgres to those would be just use unlogged tables. This is again a joke. Unlogged tables make things faster, but they have nothing to do with real in-memory databases. And adepts of in-memory databases will answer you with a joke too, like, can you do a microsecond read? Or can you do a microsecond write? Because this is actually where the border between Postgres and in-memory system goes. They can. They are very close to giving like million operations on a single core per second. And we are far away from that scale. We do give a lot of other functionalities that they don't have. But still, we can try to learn from them what they do to achieve this microsecond performance. I've tried to build my presentation upon Umbra database. This is a database by Technical University of Munich and team of Thomas Newman. It was like university, like academia prototype for researchers until it became few days ago CedarDB, which is now a commercial database. They are not open source, so I do not even consider like is it a program for computers if it's not open source? I'm not sure. But still, we have to learn, we can learn something from them. And another important aspect of Umbra is that it is not constrained by memory. It's just optimized to work efficiently when your working set fits in memory. It employs techniques that still allow them to unload data from main memory to block storage, to file system. But focus of optimization is around case, is around workload, where all the data resides in random access memory. And the key recipe for their performance is specialization of a code. From the day one, they were compiling queries with LLVM. Something similar we do for functions and for tuple deforming and different versions of hotspots in the code. But the idea of hyper and one of focuses was that you compile all the query. You compile the query in shared object, distribute it among nodes, and it's executed there. Actually, well, probably we shouldn't go that far, but how can we just prototype something close to idea of hyper? We can try to specialize Postgres code because just-in-time compilation is not the only option. For many cases, just-in-time compilation is like a trade-off. You spend a time to compile to make time of real execution shorter. But you don't know actually, do you gain anything beforehand? Maybe without real compilation, your query will be fast enough. But what we can do is like ask our compiler to work harder by giving it some hints. We can specialize the code. And here is the problem. Postgres is like Swiss Army knife. It's designed to handle all the cases of different data types and different data transformations and different joins. It's extensible everywhere and it's generic. Like it can do all the things, all the data transformations. And from time to time, we don't need it. As an example of opposite approach to generalization, we can see code from ClickHouse database, which is in turn doing a lot of specialization. In simple terms, binary of Postgres compiled is in tens of megabytes. And it's actually maybe even a lot. There were times when it was a megabyte or so. Binary of ClickHouse is in an order of 5 gigabytes of compiled and executed file. Why is that big? Because they compile all the different parts in huge chunks to help a compiler to work and optimize it in a bigger terms. So they have a data type for ClickHouse. It's not like we have input-output functions and send and receive functions, and that's it. We don't need anything to have a new type in Postgres. In ClickHouse, type is how it is added to 32-bit integer, in how it is scanned, how it's a lot of code which is special for this specific column type. And they compile functions like sum of two columns and of different types and other binary operators between possible values in an expression. So this specialization makes their binary huge, and also it makes utilizing CPU almost fully. It unwraps all the capabilities of AVX and other SIMD instructions. And when we are putting on the same hypervisor ClickHouse and Postgres, typically ClickHouse just consumes all the resources because it's specialized that way. It can take all the CPU. It's normal for analytical systems. There is a difference, but how can we specialize Postgres code? For example, let's look on our sorting code. It was designed to be specialized back in 80s. When we generate a sorting code, we actually include a template, which can take compare function as a template argument, or can leave this part to runtime call. And if we do a specialized sorting for example, for 32-bit integers, and say that in the generated sorting routine, we always have like only this function. You can inline it in a place where it's used. This gives us, on this laptop, it's about 30% faster. Like specialized code is running on tens of percent faster than generic code. This is a cost of abstraction. Actually, somewhere in Postgres code, this idea is already used. For example, here is a code, here is a commit by Thomas Monroe, which is doing only one special place in checkpointer when we need to sort out some checkpointer stuff. And it brings performance in that place. So there are actually 100 more places when we have sorting routines, which can be 30% faster, but it's not obvious because they are not like visible hotspots. What else can we specialize, for example? Most common case in relation systems is like having primary keys. Our B-tree is super abstract. It can sort ranges, it can sort geometries, it can sort texts, it can sort arrays, you name it. Like, I don't know, any data types that you can imagine already is in Postgres. And it's all the same indexing code. This is kind of cool, but what if we create, what if we look in the code? We see that we are doing this call btcompare, which is indirect call to some other place of operator class, and operator class know how to compare keys in B-tree. What we create some special B-trees for 4-byte integer, 8-byte integer, and UUID. It will cover most of cases of primary keys for many databases. Just for fun, it ought to be enough. Yeah, I wanted to make this reference. Just for fun, I tried to prototype it. I took B-tree, forked it into extension, and replaced it exactly 2 lines. 1 line, I'm not doing deforming of a tuple. I know that there are 8 bytes header, and extract value into that part. And instead of indirection call to operator class, I'm just doing compare here locally in btcompare. And here is a quick benchmark. Like I'm creating many indexes. xb3 is my forked B-tree, and you can insert 25% faster, 24, sometimes 20%. Again, we have it on a scale of tens of percents. It's not too much. I'm not sure it was effort. 24% of primary key inserts, in case of lookups, I have even less benefit, like 10% or 15%. I'm in doubts, actually. Maybe you will give me some ideas what to do with, with this idea further. And let's get back to Umbra. Another idea that is a base for Umbra is that they have special buffer manager with variable sizes of pages. They maintain virtual address space, and pages are of different sizes. And the interesting part is not just variable size of pages, that page always resides in the same address, virtual address of a process. But when they want to evict something from working set, they are doing memory advice don't need. And these addresses are still accessible. You can read them and write them, and you just will read always zeros. So you don't have that funny core dump, unless you do something strange. But you do not use operating system memory mapping for that part of your address space anymore. Well, they solve interesting problem. They solve the problem that don't have toast with these variable size pages. So the only reason to have this different size of pages is to avoid necessity of doing another layer of indirection. While in most of workloads it doesn't matter. Still, it's interesting idea that they put a lot of effort into avoiding indirection. And this is one of a cornerstone of memory databases. Postgres, being generic, is doing a lot of indirection. Indirection in comparison function, indirection in buffer management, indirection in storing long strings, and over again, and indirection of indirection of indirection, etc. Because we have to work in any conditions. They don't. But let's move on. How this works? Another idea that they build upon buffer management is pointer swizzling. What's it? Actually, pointer on a page, on like B-tree page or something like that, can be something of 64 bits. But what do they store in these 64 bits? They store either real pointer to the place in their own virtual address space, or they store identifier on how to find this exact block in file on a block storage. And to do so, they have to keep exactly one pointer on each page. So when the page is unloaded, they know where to swizzle pointer. For this reason, they have a very different B-tree locking model, but I will not go this deep right now. Well, actually, some of you are known of this picture. I've took it from OreolDB, which doing exactly the same stuff. This is a like extension for Postgres to make like to use somewhat similar ideas. There are more ideas than just pointer swizzling. They have double pointers. Currently, they have some problems with this because currently our table AM API assumes that row ID is CTID with like block number and offset number. But somehow I think this part will sort out. And why do they, OreolDB is much closer to Postgres than Umbra, of course. They want to save time for indirection in buffer manager. Because every time we go to buffer manager, first we have to grab some log, which is partitioned, but is still log. And also we have a very long buffer tag to search. It's 20 bytes or so, I don't remember exact number. It's relatively heavy and slow hash table. Probably we can make it better, but idea of Umbra and Oriol here is to just replace it with direct reference to buffer pool on pages. What I do not like about Umbra paper is that they describe like all their ideas combined, and now we have some performance benefit. I tried to separate ideas and benchmark them independently, so we can choose something to work on. Here my benchmark was relatively stupid. I couldn't come up with anything better than just adding buffer number for IndexTuple. Actually, we have here 2 spare bytes, but to have a real buffer number, I needed 2 bytes more, and I decided that, okay, I will take just 4 bytes from benchmark. And actually, B-tree code is already doing this with another candidate, checking the candidate buffer. If it is where we are going, then it's doing without much logs, just here, take it, buffer. I used simple benchmark, again, which is just inserting random numbers into B-trees. Initially, it worked somehow well. Like here is a relation of time to do insertion from dependency from the working set size to time taken by a patched version versus unpatched version. So we see that, like we can try to interpret these dots as if when we have more data, we have benefits close to like 5% of performance. But when we have more data which doesn't fit into shared buffers, we have worse performance. But remember that those 4 bytes which I added to tuple, they have penalty. So when I actually did benchmark on the server, I couldn't see real improvement. It's really not that clear that I have something good, or do I hurt the performance at all? Well, I can't prove that it doesn't work. It didn't work for me on my relatively stupid prototype. Anyway, in this idea, we have, if we want to think about it more and maybe devise some clever ideas, we should think about what we want to cache in memory and where we would like to store it. Because now I used to store buffer number, which is a purely like numbers that make sense only for this process. I used to store it on page, which will eventually hit the disk. There's nonsense with storing temporal values on a permanent storage. We could store it somewhere, maybe in special place to save, to cache some data. Anyway, going through buffer cost us something. And also, motivation behind this in OreolDB is that it scales not that good. Like you have to take logs and you have some contention on that logs. Maybe if we avoid this computation, we could improve overall performance here by jumping not by page numbers through buffer and directly from buffer to buffer. Another idea that I took from a paper about Umbra is the idea of like looking into possible different cache layouts. They refer a paper from beginning of 2000s about PAX, partition attributes across. The basic idea is that you don't store a tuple in as a continuous range of bytes. You store in a columnar way the tuple. I couldn't really prototype this. I tried, but well, it was somewhat too costly to rebuild tuple again, and we all our executor stuff relies on having this tuple together, saving these bytes together. And the main idea of this in PAX was to make projection more efficient. Some columns you just don't need to read in many cases. But still, I didn't give up on this idea at all. If we look into our page structure, really nice pseudographics from our source code, we see that we have line pointers that are in charge for tuple order on a page. And we have these actual tuples, which can be anywhere on a page. And when we are doing binary search on a page, we can effectively prefetch both possible candidates. So we don't know where we are going to go on the next step. But if we have a lot of L1 and L2 cache, we can just prefetch both of them. It doesn't. Both these lines do not block us. They are executed almost immediately, and they instruct central processor that we are going to need some other cache lines that are somewhere. But it's costly. And there is an interesting idea that is called Eitzinger layout. So when you are searching through element number 4, just imagine that this is an order of tuples on a page. When we are searching through element number 4, next our key lookup will fall either on tuple number 2 or tuple number 6. If we have them in the same cache line, we can try to prefetch it with just one built-in prefetch. And this will alleviate the need to do two prefetches. We will touch this cache line anyway for one tuple or another. So we can arrange tuples on a page in a manner that is cache-friendly. But there will be but later. Some nice chart from scientific papers. I imagine like I am scientist, so here are papers and charts. Of course it works somewhere, they published it. But the interesting part is, does it work for us? Thinking about it, I had 3 different ideas. First one was like strategy, like in-order strategy. Basically no strategy. Third strategy is Eitzinger layout, which I was discussing just before. And another one is 1MDBOS layout, and it assumes that we can try to prefetch always left turn. Look at this tree of binary search. We can pack 8, 4, 2, 1 together. And if we are lucky, we don't need to do any prefetching at all, because when we touched cache line for key 4 at tuple 4, we already prefetched cache line at tuple 2. So it is like more cache-friendly layout and no need to temporal prefetches. To do temporal prefetches. I benchmarked this stuff. Problem, but which I was referring to before. Any insert, any delete, anything you do with tuples on a page, and now binary search will operate differently. It will hit another tuple offset numbers, and it doesn't work anymore. Anyway, I created some benchmark. Not me, of course. Someone 20 years before me created pgbench, and at most I got 2.5% of speed up here using like more friendly B-tree caches. Again, it's not that much, 2%. Does it worth effort? Probably, but it's complex, and its effect is destroyed with every single update. As far as I remember, it was reading workload. By the way, I installed code which is doing this arrangement of a page into vacuum. So when you just vacuum a B-tree page, you have that cache-friendly order, but any modification, you don't have it. Like, you just lost 2%, not that much. Okay, another stuff that is there in Umbra, and I failed to prototype entirely, is optimistic buffer locks. How it could work? When we start to look at the page, we don't lock anything. We just read through the page, even without locking the buffer. We must be prepared to some unforeseen consequences, especially if there are some offset numbers, because they might be corrupted in terms of our scan of a page. As was mentioned in some previous sessions, it's easy to get check crashed with some specifically crafted page. The same goes with this lockless access to the page. Anything you do wrong, like moving bytes under scan, and core dump. So this part is actually undoable in my practice. Maybe you will be more lucky. And then the idea is that you check LSN after scanning a page, and if it changed, obviously you have to discard result of a scan and rescan it again. What we save here? We save time to lock the buffer and contention of a buffer. Again, this is the very same idea around same subsystems in a database. Problems that we have here. Well, we have separation of responsibilities in our code. We are passing pointer to the datum, to the actual datum, to operator class. And if something changed under the wheels, many things can go wrong, not in a B-tree code, but in operator class code, and it's just too hard to be prepared on foreseen consequences everywhere. Like I see those who was playing Half-Life. Well, another problem is that you have ABA problem at full scale, because you can read LSN from page, then buffer manager replaces it with something else. You are thinking that you are doing actual scan, then buffer manager replaces it back with a page, and you don't see that anything changed because it changed back. So I found that this idea is just nearly impossible to prototype in Postgres. Some conclusion. Together, these ideas might constitute, like, they might add up with this percent, like 10% here, 2% here, 5% there. All in all, we can, like, maybe 50% or so accumulated. I'm not sure, I didn't try all together because every single patch actually worked not well. But some ideas might be used in other subsystems or maybe even pushed further to some more realistic implementations that I did. I will happily share the code of anything I demonstrated. It's all on GitHub already, but it's a little messy. Overall conclusion is, let's look to ideas in other databases. They are fun, at least to know that they are doing some insane stuff like reading without logs, maybe like concurrently reading without logs. Maybe we could have something useful out of it. And thanks for listening. I'll be happy to discuss anything with you. Anyone ready to try it on your production servers?
Not ready, but I have a question. Did you also try to just order the tuples in the same order as pointers?
Yes, actually this, if you follow this link in Hackers, there was extra line with ordered, and I saw no statistical difference between just random.
Yeah, I think the ordered one that some early experiments was useful for sequential scans. There you could see difference, not PGBench where you are doing index lookups.
We already have this code that is, the function is called repair fragmentation, so in heap. And it's already arranged in tuples in order. So
does it make them in the same order now? Yeah.
Yes.
Okay. Okay.
Yes, but don't trust me. I think so, but maybe.
I remember when it was first done, the kind of the new way of heap fragmenting. Then it originally didn't do. I remember suggesting that it should, but I didn't follow up if they actually changed.
Let's just see the code.
Order into the item. You are saying that ordering the tuple into the item pointer order, right?
Yeah. Yes.
They don't do actually.
Okay.
When we implemented some other storage like Z, you might have heard sometime. That time we have done that optimization of ordering into the item pointer order also, and we found some performance improvement there. But independently, we did not contribute that to actual Postgresql code. I think don't have that arrangement.
Look, it's scanning tuples in order of set numbers. And I don't know what is going on. It's just too much of a code to deal with it online. Maybe we could understand it from comments, but let's do it in offline discussion. I think we can find out if it works and maybe even benchmark it here. Not that difficult. Yeah?
Yeah, I don't understand pointer swizzling, but I'm just puzzled by the fact that you store the virtual address of the page in the page tree. What happens if the page gets evicted and then that address would be invalid?
Well, in Umbra, if page is evicted, you still can read the same pointer. Like you will just get zeros from it. Well, to read a page, you need to load it. To actually read, you need to load it in memory, and it will be at the same place where it was pointing by a pointer. So it will be loaded in the same address of virtual virtual address space. But actually, swizzling is just looks to me overly complicated. Like as someone who is looking through Postgres code, I mean, overly complicated is really overly complicated. Like they are changing locking model of B-tree to ensure that you always have just one pointer to every page. So when you want to make it file system resident, to unload it from your memory, they are swizzling that pointer back to number of a block in a file on a file system. So
I think also Oriole example was slightly more complicated, where they had immutable pages. So a page can be, like if you had a sibling and you load it in memory, that's the only time you update the pointer. It can never switch back. So the buffer eviction resulted in like requirement to have either a new version of a page or some complicated mechanism.
it's as far as I remember, it is used for checkpointing. Actually, Umbra do not describe their recovery model much. They have like 20 lines that essentially say, we have arrays, and that's it. That's it. I don't know how they do checkpoint. Probably we will see more because now they are like commercial database, not just academic prototype, and they will have to like document how it works, and we will see some more ideas from their documentation.
So an idea that was floating around like a lot in the in-memory space a while back was having all operations on tuples be done in like batches for better like iCache and Dcache efficiency. Is that like something that's done in Umbra, or
Sorry, didn't.
so that having operations be performed in batches rather than everything being like tuple at a time?
I still don't get the idea. What?
Maybe we can talk afterwards.
I'm suggesting that query execution would process, instead of a tuple, would process a batch of a tuple. Yeah, I was at Microsoft when column store was implemented, and there was in order to test executor executing on tuples versus batches of tuple, they built a system that was operating on top of heap instead of a column store, and with a SQL server, which was highly templatized in C++, they have seen 30% performance improvement on that. So there's definitely a lot of efficiency left.
So if there are 30% more, we should discuss it more. Yes?
Yeah, I do find this fascinating because for years I used to get the question, do you have like an in-memory mode, right, for Postgres? And I used to say, well, I would always kind of thrown off, and I used to ask the person, what is it that you want that an in-memory database does? Aside from the fact that you're limited to RAM, right, which is the problem with in-memory, like what feature are you looking for that Postgres doesn't have, because it does stuff in memory and then it spills the disk. Like, and I could never get an answer from anyone. But I guess what you're saying is there are certain structures that can be only done by in-memory.
No, I am trying to move the structures to our code too.
Right, that's what I'm saying, right.
Yes.
But what is it about in-memory databases specifically that people feel like they're missing when using Postgres? And nobody's ever been able to explain it to me, except that it's some kind of buzzword, right? Which
It just sounds like it sounds fast and it must cost some money.
And you can get rid of some of the state, like suppose we're having the buffer mapping hash table, which is required because we are sure that all the pages are not in the memory.
Okay.
Right, but if you have only in-memory database, then you don't need this sort of buffer mapping hash table because everything is into buffer pool. You should be having, like, you can directly look your buffer into somewhere into
it's
the
not going
cache.
to move around,
Right, right.
But the question I've always had, which you really covered well, is, okay, so I understand that would be a benefit. There's a disadvantage because now I can't spill the disk. What is the benefit of doing that? And what it sounds like you're saying is the benefit's kind of like, it's kind of hard to see. It's a couple percentage points. And I was like, wow.
And I also think he said that you actually can split it because you can kind of punch holes that memory is not used, and then you still have this advantage that the hash table is actually your virtual memory table.
Okay.
And then whatever gets moved away appears as zeros, and then you may want to load it back.
The real advantage of in-memory databases in terms, not how it works, but what it is a microsecond writes. They can do it, we can't. We should work to get to this microsecond. I don't know how. We surely can. like combine all the stuff like prepared statement and pipelining and like working on like Unix socket and doing better cache, more cache-friendly algorithms, less locking, all the stuff. Why is this maker-second is important? Because it unlocks other patterns. Like we cannot do a cache of cookies in Postgres. Like we can, unless we have millions of requests per second to a single server. It would extend our use cases even more. Like Postgres is almost everywhere. If we get this microsecond, this is from a bottom part, and also petabyte scale, we will be everywhere literally. Like there will be almost no use cases which cannot be covered by Postgres. But it's still a lot of effort to get to this microsecond.
I guess my question is, if the working set already fits in RAM, don't we have microsecond writes now and reads?
We will have time to plan. Our like network pipelining is not that good. No, we don't get this microsecond. Maybe we can like benchmark it more, but some other databases will be better at doing cache as a service. And if we are doing highly concurrent operations, there is a room for improvement, definitely, at least for a couple of tenths of percents, but maybe more.
Okay, thank you. This is very helpful.
That was my attempt to implement the same ideas, but maybe someone more like stubborn will get this even further. Yes?
One similar thing, I'm not sure it's exactly the in-memory database, but we have a customer case. The customer was doing something that was not really very smart. They pulled 100,000 rows to the microservice, and they wanted it to be done in something like 0.1 seconds. And it appears that they were able to do it inside Oracle. And in Postgres, it just doesn't happen. You can't get that many out there that fast. But you can do it, it's just memory.
And also, other databases have other data model, which is really important to have this microsecond. Okay, so thank you for listening. I'm happy to be here.